Today, I'll explain how I implemented the Screen Space Ambient Occlusion effect for my upcoming game Brobot. This effect approximates the occlusion of ambient light in real time. You can think of it as a simulation of diffused shadows caused by objects in proximity. SSAO will darken an object within its crevices and the corners of a room. We create two render targets with an internal texture format of GL Red. We only need one color component because we're producing a monochrome output. The first render target will apply a rough first pass of occlusion shading. The second will smooth out the first by applying a blur. In the OpenGL client, we pass through a position map to specify the position of each pixel, a normal map to specify the direction each pixel is facing, a noise map, and a pixel sample array. The latter two will be explained shortly. In the pixel shader, we create a TBN matrix to transform the pixel from tangent space into view space. Tangent space is the local coordinate system associated with each pixel. View space is the perspective of the viewer of the scene. The TBN matrix is comprised of three vectors that are orthogonal to one another: the tangent vector, bitangent vector, and normal vector. We use the noise map to randomize the tangent vector. We then calculate the bitangent vector by taking the cross product of the normal and the tangent. By randomizing the tangent vector, we smooth out the banding that would be introduced by us taking a tractable amount of samples. To create the noise map, we generate 16 random vector 3 values between -1 and 1 for the x and y components. We set the z component to 0. We take 64 randomly generated samples around the pixel that lie within a hemisphere oriented by the TBN matrix. This ensures that we do not sample depth values behind the pixel. Next, we project the sample position into screen space to get the depth value. We use a range check to ensure that we are not testing the pixel against others that are too far away from it. The smooth step function allows this check to be smoothly interpolated to prevent a hard edge when a pixel is out of range. The bias helps us to modulate the intensity of the effect by offsetting the sample depth. In the second render target, we will blur the effect created in the first render target. This will ensure that it looks smooth. In the OpenGL client, we pass through the texture created by the first render target and the textile size. In the pixel shader, we perform the box blur.